Lecture 2.10, the Lorentz transformations. In the last chapter, we derived the Galilean transformations, which show us how to measure the positions of an object as measured in a moving reference frame relative to one that's in a stationary frame, where the moving one has a velocity v with respect to the ground. In this lecture, we'll derive the Lorentz transformations, which are a set of transformation equations that satisfy Einstein's postulates that 1. All inertial reference frames are equivalent, and 2. The speed of light is constant for all reference frames. So we'll go through this step by step. If you're not interested in the derivation and you just want to move on to application, you can probably skip through most of this lecture. We're going to use the Galilean transformation equations as a guide. Because the primed frame is moving along the positive x-axis with respect to the unprimed frame, we'll assume that the y and the z components are not affected by that relative motion. We'll also assume that the x prime and t prime coordinates are linear functions of x and t, and vice versa, x and t are linear functions of x prime and t prime. Because we're assuming that the t prime frame is moving in the positive direction with respect to t, we get a negative sign in front of the t coordinate, whereas we get a positive sign in front of the t prime coordinate. The coefficient in front of x is going to be the same as the parameter in front of x prime, and the parameter in front of t is going to be the same as the parameter in front of t prime. So in any case, this is the general form of the transformation equations that we're going to be looking for, and our job is to solve for these unknown constants a, b, e, and f. Okay, so we're going to use some different constraints for the equations. So, for example, along the ct prime axis, where x prime is equal to 0, if we start with our general transformation equation, x prime equals ax minus bt, you plug in x prime is 0, so this is 0. And we solve for x, so x is equal to b over a times v. Well, that's b over a is just going to be the velocity of the relative velocity between our moving coordinate frames. So in other words, b over a must just be equal to the velocity, or b is just equal to v times a. Next, let's use a constraint for light rays. So we'll have that x is equal to ct, where c is the velocity of the light ray, and x prime is also equal to ct prime. So this assumption right here gets at Einstein's second postulate, that every observer sees the same velocity of light. If this was Galilean relativity, you'd have to add in the velocity of light plus the relative velocity of the two coordinate frames. But that's not here. This is saying that the speed of light is constant for everybody. So we can make these substitutions, and our previous result, that b is equal to v times a, plug it into our transformation equations. We're plugging in ct for x and ct prime for x prime. We're also plugging in that b is equal to va. Okay, so now we're going to solve for t in this bottom equation. So if you divide this bottom equation through by c, and then take what you have for t and plug it in here, then this top equation becomes ct prime equals a c minus v here, and then this t part is going to be this equation here after you divide through by c. So 1 over c, a, c plus v times t prime. So we actually eliminated t between the two equations first, but now notice that the equation that we get left over, there's a t prime on each side. So you can actually eliminate t prime as well. So if you divide the left and the right by t prime, you can solve for the a constant. So we're going to divide through by ct prime, the t primes cancel, and then you rearrange the algebra, you get 1 equals a squared times the quantity of c squared minus v squared. Solve for a, you get that a is 1 over the square root of 1 minus v squared c squared, or v squared over c squared. So this should look familiar. This is the gamma factor that we saw when we were studying length contraction and time dilation. So this a constant in our equations, we can just write that as gamma now. So if we combine all of our results, we saw that these general equations like x prime equals ax minus bt can be written as gamma times x minus vt, and x equals gamma times x prime plus vt prime. So these two equations right here are two of our Lorentz transformations given that gamma factor. I'll leave it as homework to show through a very similar calculation. You can do something similar for the t prime and the t equations. So the t prime equation looks like this. The t one looks like that. So we can now summarize the results. These are the Lorentz transformations. The left side lets us calculate the primed coordinates given the unprimed values. And the right equations let us calculate the unprimed given the primed. Sometimes when you're doing calculations, it's easier to work with CT instead of just time and beta instead of V over C. So if you make these substitutions, you can write the Lorentz transformations in a slightly different form. So here, the minus VT turns into a minus beta CT. The T prime is now a CT prime. Anyway, so if you like working with CTs and betas, then here's an alternate form of the Lorentz transformations. It's all exactly the same, just notation is different. Okay, so now we're going to construct a Minkowski diagram for showing what these Lorentz transformations are doing. So we're going to start with a space-time diagram in the O frame. So the horizontal axis is going to be x, the vertical axis is ct. We first want to see how to represent the ct prime axis on this diagram. So the ct prime axis is defined by x prime is 0. If you use this Lorentz transformation equation, plug in x prime of 0 here, then that gamma factor can be divided into the 0. And if you solve for t, you'll just get x minus vt equals 0, solve for t, it's going to be 1 over v times x. If you multiply both sides by c, then you get that alternate form that ct is beta, that ct is x divided by beta. So in other words, the slope of the ct prime axis is going to be 1 over beta. So if we plug in, say as an example, that beta is equal to 1/2, then the slope of the ct prime axis will be 2. So here's the ct prime axis. In step 3, we construct the x prime axis. It's very similar to constructing the ct prime axis. So the x prime axis is defined by ct prime equals 0. Use Lorentz transformation, plug in ct prime as 0, and find the relationship between ct and x. So here, the coefficient or the slope is going to just be beta, or v over c. So we can construct the x prime axis like this. If beta is equal to 1/2, then the slope of the x prime axis is 1/2. All right, step 4, we now figure out what unit tick marks are along each of these axes. So first, let's start with the ct prime axis. Again, remember, x prime is defined by 0 to define that axis. we want to figure out where a tick where CT prime equals 1 is. So we solve for X and CT for CT prime equals 1. So again, use Lorentz transformations. So we plug in 0 for X prime, and we're going to plug in 1 for CT prime. So when CT prime is equal to 1, X is going to be gamma V over C, or in other words, gamma beta. Similarly, for time, we use this Lorentz transformation. Same thing, plug in the values, and we find that T is equal to gamma T prime, or CT is equal to gamma CT prime. Plugging in CT prime of 1 tells us that the CT coordinate is this gamma. So to summarize, the unit tick mark along the CT prime axis has coordinates gamma beta comma gamma. So when beta is equal to 1/2, then the position of that unit tick mark is 0.57 comma 1.51, and we can locate that on the diagram like this. So when X is equal to 0.57, that's going to be like right in here someplace, and CT is 1.15, so it's like right in there. So that's the unit tick. So to find out where 2 is, where CT prime equals 2, and then you just like double it going up the CT prime axis. Okay, so now we've defined the CT prime axis, and we know what the unit tick marks are. Step 5, exact same thing with the X prime axis. So follow the steps, plug in X prime of 1, use Lorentz transformations, and at the end of the day, you can show that the coordinates of the tick mark, the unit tick mark along the X prime axis is gamma comma gamma beta. So they're just reversed. So now the X coordinate is 1.15 and the CT coordinate is 0.57. So there's the tick mark for the unit value along the X prime axis. All right. Well, now that we've got our axes and the tick marks, we can draw in grid lines just by creating lines that are parallel to the CT prime or X prime axes. So to construct lines that are parallel to the CT prime axis, where X prime equals like integers 1, 2, 3, 4, we just find our tick marks and then draw a line that's going to be parallel to the CT prime axis. So along this line, X prime equals 1. Along this line, X prime equals 2. Along this line, X prime is negative 1. Do the exact same thing for the lines parallel to X prime axis. They look like that. And there we go. We've constructed what space-time looks like in the moving frame mapped onto our CT X axis. So how do you use this kind of diagram? Well, so for example, if you knew the coordinates of a point in the Minkowski diagram, so if X prime is 2 and CT prime is 1.2, you can draw that just by using our normal X and CT axes. So there's 2, and then this one, bring it over, that's got a coordinate of 1.2. So that's how to locate it just in our regular unprimed frame. To read off what the primed coordinates are, well, you just extend a line. If you wanted to read off what the CT prime value is of this point, you would just extend a line parallel to the X prime axis until you run into the CT prime axis. And then try to, kind of read off, try to estimate where it is. So, this looks like it's about maybe 0.2 of the way from 0 up to the tick mark. So I would, just from the diagram, I would estimate that it's around 0.2. If you use the Lorentz transformation and if you plug in CT equals 1.2 and X equals 2, then you get that it's 0.23. So we were pretty close in our estimation. So it turns out to actually be 0.23. Same if you want to read off what the x prime axis is, you draw a line parallel to the CT prime axis until you run into the x prime axis and again try to read it off. So here's 1, there's 2, so maybe you're at 1.6. And then if you actually did the math, plugged it into the Lorentz transformation, it would be 1.62. So again, pretty close. Okay, so now let's look at, let's kind of animate some of the stuff to kind of put it in motion, see what it looks like. So let's locate a point in the unprimed frame with coordinates 3, 2. So there's the point. And we want to do, so you can kind of read off the values along the x and CT axes like that. If we want to read off the coordinates in the moving frame, in the primed frame, well, let's see here. We can construct our axes, overlay the coordinates. Like that. And again, we want to just read, if we kind of draw lines parallel to the CT prime and x prime axes, we can read off the values again like we just did. So we see that the x prime value is about 2.31 and the CT prime value is about 0.58 in this example. So the other thing we can do is kind of vary the velocity, the relative velocity between the moving frame and the rest frame, or between the unprimed and primed frames. So we start with a value of around of beta's 0.5, and you can see how those two, the x prime and the CT prime axes, kind of fold together in the limit that the velocity approaches the speed of light. The x prime axis and the CT prime axis will be on top of each other along the diagonal. If we reduce the velocity back down to 1/2, about 0.25, and then back to 0, we see that the primed axes just lie on top of the unprimed axes. And if you go to negative values of velocity, the axes shift into the second and fourth quadrants. So as you go to a very large negative velocity close to the speed of light, the prime axes now go along the diagonal with a slope of -1. All right, we can do the same thing again by overlaying our grid. So here is a representation of the grid of space-time values. Again, by changing the velocity, you can see how space and time warp into each other. And this warping of space and time that you're seeing here in these Lorentz transformations, this is really, this is the heart of what special relativity is describing. Okay, so in the next lecture, we will give some examples of how to use Lorentz transformations in solving problems.